The future is being written in silicon. Advanced computer chips are the engine of progress. They power everything from smartphones to supercomputers. Big data, artificial intelligence, and high-performance computing all rely on these tiny marvels. As we demand more from our technology, the pressure is on to design even more sophisticated chips. This is where the world of semiconductor design is undergoing a revolution. The stakes are incredibly high. Whoever controls the design and production of these chips holds the keys to technological dominance. It's a race with far-reaching implications for economic prosperity and national security. In this rapidly evolving landscape, a new player has emerged: artificial intelligence. The global landscape of chip design is dominated by two superpowers, the United States and China. The US has long been the industry leader. American companies boast a commanding share of global chip design sales. They also dominate the market for electronic design automation, EDA tools, the sophisticated software used to design these chips. China, however, is rapidly catching up. The Chinese government has poured billions of dollars into its domestic chip industry. The goal is clear: to achieve self-sufficiency in semiconductor technology. Chinese companies are making strides, particularly in areas like mobile chips and consumer electronics. The competition between these two giants is fierce, with each side vying for technological supremacy. Artificial intelligence is poised to revolutionize the way chips are designed. This groundbreaking technology is not just a tool, but a game-changer in the semiconductor industry. Traditionally, chip design has been a laborious and time-consuming process. Engineers have to meticulously plan and execute each step, often dealing with complex calculations and intricate designs. It involves countless hours of human ingenuity and expertise. Teams of engineers brainstorm, sketch, and iterate to create the perfect chip design. But the increasing complexity of modern chips is pushing the limits of traditional design methods. As chips become more advanced, the design process becomes exponentially more challenging. This is where AI comes in. AI has the potential to transform this intricate process by introducing efficiency and precision. AI algorithms can analyze massive datasets, identify patterns, and make predictions with remarkable accuracy. They can process information at speeds and scales that are impossible for humans. In the context of chip design, this translates to faster design cycles, optimized chip layouts, and improved performance. AI can help engineers achieve results that were previously unattainable. Imagine AI algorithms sifting through billions of potential circuit arrangements to find the most efficient design. This level of analysis would take humans years to accomplish. Or picture AI tools automating repetitive tasks, freeing up human engineers to focus on higher-level design challenges. This not only speeds up the process, but also allows for more innovative solutions. The integration of AI in chip design is just the beginning. As AI technology continues to evolve, its impact on the semiconductor industry will only grow, paving the way for the next generation of technological advancements. To understand AI's impact, it's crucial to grasp the sheer complexity of chip design. A modern chip can contain billions, even trillions of transistors, all interconnected in intricate ways. The process of designing these chips is broken down into multiple stages, each with its own set of challenges. One of the most complex stages is called floor planning. This involves deciding the physical placement of different components on the chip. The number of possible arrangements is astronomical. Imagine trying to find the optimal arrangement of pieces on a chessboard, but with billions of pieces instead of 64. It's a problem of mind-boggling complexity. Section 5, where AI falls short and where it shines. While AI offers tremendous potential, it's not a silver bullet. The technology has its limitations and isn't always the perfect solution for every problem. Current AI algorithms still struggle with certain aspects of chip design. They often lack the nuanced understanding that human engineers bring to the table. For example, they may excel at optimizing for a single objective, like performance, but they often fall short when it comes to balancing multiple conflicting constraints. Engineers frequently have to consider a variety of factors, such as power consumption, physical size, and cost, all at the same time. This is where AI can struggle. A chip might need to be designed for high performance, low power consumption, and a small physical size. A complex balancing act that AI finds challenging. This balancing act is crucial because the success of a chip often depends on meeting all these criteria simultaneously. However, AI shines in specific areas. It excels at tasks that require speed and precision, which are often time-consuming and error-prone for humans. For instance, AI can rapidly perform design rule checking, a task that involves ensuring that the chip design adheres to a set of predefined rules. It excels at tasks like design rule checking, where it can rapidly identify potential violations in the design, saving engineers a significant amount of time. This allows engineers to focus on more complex aspects of the design, knowing that the AI has handled the more routine checks. AI can also optimize power consumption by intelligently routing signals and managing voltage levels, which is crucial for creating energy-efficient chips. Moreover, AI-powered tools are emerging that can automatically generate test cases for verifying chip functionality, a crucial step in the design process. These tools can identify potential issues early in the design phase, allowing for quicker iterations and more robust final products. In summary, while AI has its limitations, it also offers significant advantages in specific areas of chip design. Section 6. A hybrid future blending AI and traditional methods. The most promising path forward lies in hybrid approaches that combine the strengths of AI with traditional design methods. This involves using AI to automate specific tasks and assist human engineers, rather than replacing them entirely. For instance, AI algorithms can generate initial design layouts, which experienced engineers can then refine and optimize. This collaborative approach leverages the unique capabilities of both humans and machines. Human engineers bring their creativity, intuition, and years of experience to the table, while AI provides raw computational power, speed, and the ability to explore vast design spaces. Section 7. The evolution of chip design, new architectures and beyond. The world of chip design is not standing still. With each passing year, the demand for more powerful and efficient chips continues to grow, driven by advancements in technology and the ever-increasing need for computational power. Moore's law, the famous observation that the number of transistors on a chip doubles approximately every 2 years, is reaching its physical limits. As transistors become smaller and more densely packed, we face significant challenges in terms of heat dissipation, power consumption, and manufacturing complexity. This has led to the exploration of new chip architectures and design paradigms. Engineers and researchers are now looking beyond traditional silicon-based designs to find innovative solutions that can overcome these limitations. Instead of relying on monolithic CPUs, the industry is moving towards specialized chips optimized for specific tasks, such as graphics processing, artificial intelligence accelerators, and even neuromorphic computing, which mimics the structure of the human brain. These specialized chips offer significant performance improvements for their intended applications. Neuromorphic computing in particular represents a fascinating frontier. By emulating the neural architecture of the human brain, these chips have the potential to revolutionize fields such as machine learning and artificial intelligence, offering unprecedented levels of efficiency and processing power. These new architectures present both challenges and opportunities for chip designers. On one hand, they require new design methodologies, tools, and expertise. On the other hand, they open up possibilities for creating more powerful, efficient, and versatile computing systems. AI is playing an increasingly important role in designing and optimizing these complex systems. Advanced machine learning algorithms can analyze vast amounts of data to identify optimal design parameters, predict potential issues, and suggest innovative solutions. For example, AI algorithms are being used to develop new materials and fabrication techniques that can push the boundaries of chip performance even further. By leveraging AI, we can achieve breakthroughs that were previously unimaginable, paving the way for the next generation of high-performance computing. Section 8. The Geopolitics of Semiconductors. The geopolitical implications of semiconductor technology cannot be overstated. Semiconductors are the lifeblood of the modern economy. They power everything from smartphones and laptops to cars, airplanes, and advanced weapon systems. The ability to design and manufacture advanced chips is therefore a strategic asset of immense value. The US-China rivalry in chip technology is a major geopolitical fault line. Both countries recognize the strategic importance of semiconductors and are investing heavily in domestic production and research. This competition has led to concerns about supply chain disruptions, technology decoupling, and even the potential for conflict. Section 9. The future belongs to the bold. The future of chip design is being shaped by the convergence of AI, new chip architectures, and geopolitical competition. Those who can master these forces will be the ones who define the technological landscape of the 21st century. This requires a commitment to innovation, collaboration, and a willingness to embrace new ideas. The challenges are immense, but so are the potential rewards. Advanced chip design is the key to unlocking breakthroughs in artificial intelligence, medicine, energy, and countless other fields. It is a field ripe with opportunity for those bold enough to seize it.